Big data analysis in the context of smart tire development. Tire Technology Expo Conference 2025, Deutsche Messe, Hanover, Germany, March 4th. Hello everyone, my name is Dan Andre Anton. My background is in automotive engineering. With over 17 years of experience in R&D and project management, I have a proven track record of delivering innovative projects for the automotive sector. I have worked so far with many stakeholders, including automotive OEMs and Tier 1 suppliers, like tire makers, so I know the challenges related to both part and system design engineering. To validate tire designs, manufacturers must test tires physically or, in the best case scenario, by using virtual technology. At Unleashed Engineering, we generate value by streamlining the R&D of smart tires for electric vehicles. We do this with modern engineering and effective and efficient data management. Last year, I discussed how sensors can be mounted in tires in a first mounting scenario. A TPMS sensor, an ID tag, and acceleration sensors can be encapsulated in a sensor container which can then be attached to the tire's inner liner. I emphasized the importance of carefully considering the geometry and discretization method and setting up the correct boundary conditions to ensure the system operates flawlessly. In this scenario, the special sensor, or what we can call a generic TPMS sensor, was modeled with two potential ID tags at different locations. After modeling, it was attached to the inner liner in the middle of the crown or the tire's cross-section. Additionally, two acceleration sensors were modeled on the ID tags to assess acceleration levels during footprint events. I described how to handle sensor signal data from a smart tire. The structural analysis of the initial sensor mounting scenario can be further enhanced by embedding additional sensors such as acceleration sensors and by analyzing their signals in real time. Sensor signals allow us to run extensive design of experiments to cover various load case scenarios to study the impact of dynamic parameter variations. Parameters such as inflation pressure, tire loading, speed, tire slip angles, and tire slip ratios can be all considered. Additionally, design sensitivity analysis can be conducted by adjusting the position of the embedded acceleration sensor within the generic TPMS sensor. We have observed that the acceleration signal is sensitive to the sensor's embedded location. So now, a bold question arises. What if smart tires become super smart tires next? Imagine having more than one data point from inside the generic TPMS sensor. This is where we introduce the so-called virtual intelligent tire belt, which can be considered the next generation tire mounted sensor containing a cluster of 6 sensors for now. This virtual device aims to collect much more data about tires in real time. It could be connected to a TPMS sensor and contain 4 additional acceleration sensors to record more data from the tire crown and tire sidewalls. If smart tires become super smart, then large DOEs will become the new norm in tire analysis, and we will have to process a huge amount of sensor signals data. If you do the math with this new scenario, we have 18 signals from the 6 acceleration sensors, each node having 3 axes, X, Y, and Z. Depending on the DOE, one may consider vertical loading, inflation pressure, and speed as the first parameters to consider as variable. This means we will have 144 datasets as raw data, times 2, that is 288 datasets if we want to filter data, or times 3, which is 432 datasets if we want transform data as well. For one tire design iteration, that is already a huge amount of data. The key message here is the fact that one sensor only could generate many signals depending on the load case, and this would be very hard to manage manually. Here, for instance, we see the effect of vertical load and speed variations in 4 loading conditions. For each of the load cases, we can choose to look at raw data only, filtered data, or transformed data. These first sets of signals are all for 2.0 bar inflation pressure. These second sets of signals are all for 2.5 bar inflation pressure. As we can see, the inflation pressure impact is well captured by the acceleration sensors in any of these 4 load cases. Going deeper with the analysis, we can overlay one or more signals to better capture the impact of one or more testing parameters. For instance, we can overlay the data output for 2 different load cases or more and focus only on the transformed acceleration datasets in G units. Same as above, the inflation pressure impact is well captured by the acceleration sensors in any of these 4 load cases. As we have already seen, one sensor mounted on the tire's crown can already be the source of a lot of data. This means that multiple sensors will generate a huge amount of signals. If we isolate the local X acceleration signals, we can start identifying which of the 6 sensors is relevant and in which load case context. We observe a correlation for the first 2 sensors, 1 and 2, mounted in the middle of the crown, showing the highest sensor's peaks. We also capture the effect of positioning inside the generic TPMS sensor. We see nearly zero accelerations for node 3 and 6 mounted on the sidewall, and similar acceleration levels for nodes 4 and 5 mounted under the tire's shoulders. If we isolate the local Y acceleration signals, we can start gaining more insights regarding the local or global lateral accelerations. By global accelerations, we mean the accelerations with respect to the center of the tire. Similar correlations are observed for nodes 3 and 6 mounted on the sidewalls, and for nodes 4 and 5 mounted under the tire's shoulders. This was expected since we know that a tire's structure is symmetric when referring to its left and right halves. If we isolate the local Z acceleration signals, we get perhaps the most relevant and expected acceleration signals. They all correlate with the radial deformation, which is the most obvious and expected deformation before the lateral or longitudinal deformations. Again, similar and expected correlations are observed for nodes 3 and 6 mounted on the sidewalls and for nodes 4 and 5 mounted under the tire's shoulders. I believe that these signals can play an important role in developing future ADAS algorithms. The tire load, tire wear, and many more insights such as wheel alignment could potentially be derived from processing these real-time acceleration signals. Now, since we have much more sensors to account for, the question is how can we manage this new big data context? Managing the influx of data from multiple sensors can indeed be challenging, but streamlining the process with a well-defined workflow can make it more manageable. Here is how a new workflow can help the engineers perform faster. In step 1, in the model creation phase, We develop a detailed model that accurately represents the system and its components. In step 2, we run the simulation to generate the data based on the model. In step 3, we write scripts for processing the raw signals from the sensors. In step 4, we are running the scripts or executing the scripts to analyze and interpret the sensor data. You can also export the process data for further analysis or reporting in a step 5. Optionally, you can export databases from the simulation containing just the sensor signals, and you can also automatically generate reports based on the processed data. In this video, we see a demonstration of a script used to automatically post-process acceleration signals. The tool takes the simulation results, loads the sensor data, and processes their signals in real time. As we can see, one or more load cases can be considered simultaneously. During the running of the script, we can view the data in various ways. As mentioned before, we can either process raw data only or directly request filtered or transformed data. Additionally, we can request to write back the post-processed data in different formats, as pictures of signals, or multiple overlaid signals, or as XY text data to be used in machine learning algorithms, for instance. In conclusion, we've seen how a smart tire system model can potentially be transformed into a super smart tire with additional sensors mounted in a virtual intelligent tire belt. Various sensitivity parameters have been tested to validate the virtual intelligent tire belt, including inflation pressure, vertical loading, speed, and even the acceleration sensor position inside the generic TPMS sensor. As further developments, we can foresee working in partnership with tire makers, sensor makers, and even car makers to explore the opportunity of obtaining synthetic data from virtual sensors analysis for ADAS algorithm development and other tire-related applications. We also aim to extend the modeling and analysis from the tire subsystem to vehicle systems design engineering approach to research dependencies between tire states and the rest of the vehicle's chassis and suspension components. I believe it is very likely that we will be able to predict the tire wear state and even tire forces and moments based on these processed signals coming from tire sensors. Ultimately, it is very likely that we will develop predictive tire characterization and tire performance algorithms based on virtual sensor data. Thank you for your time. You can connect with me using these coordinates.